Hi students, in this video we are going to see about the color of the complex, color like how the D block elements produces colors and also the other properties. Okay, so let us see one by one. So here like you know like we have the elements, right? Scandium, titanium, vanadium. For example, 3D series if you take, you have like scandium, titanium, vanadium, chromium, manganese, then iron, cobalt, nickel, copper, zinc. So you have some colored elements also here, right? As such the metal are colored, right? Copper is colored, for example, right? So here we are going to see about ions, how they are colored here. Is it okay? And simple logic behind the color of how to find the color of the ions is D0 and D10 are colorless. Okay, only these two cases. Only in these two cases ions are colorless. Other than that, D1, D2, D3, D4, D5, D6, D7, D8, D9, they are colored. Okay, for example, scandium 3+. How to write the electronic configuration for ions? You know, for scandium it is argon 3d1 4s2, right? For scandium it is 3d argon 3d1 4s2. If it is scandium 3+, what do you mean by 3+? 3 electrons lost, right? So 2 electrons from here and 1 electron from here is lost. So it becomes 3d0, no, no. So it is colorless. Okay. Scandium, argon, 3d1, 4s2, you know, and scandium 3+, from always you should remove from 4s and then only 3d. You should never directly remove the electrons from 3d. Always remove from 4s, then come to 3d. Is it okay? Now 3d is 0, so therefore it is colorless. Similarly, titanium. Okay, so you know atomic number is 22. Argon 3d2 4s2. Okay, so titanium 4+. So what happens? 2 electrons from here goes, 2 electrons from here goes. So it becomes 3d0, which is colorless, right? So what we know now? If it becomes 3d0, definitely it will become colorless. Is it okay? Similarly, Cu+. Okay, now we are going to write for Cu+. Copper, what is the electronic configuration? Argon 3d9 4s2. Okay, 3d9 4s2. But you know very well how we should write. The correct electronic configuration will be always it is 3d10 . So if it is plus means what we are supposed to do? We have to remove electrons from 4s, right? Now it is completely filled. If you take d orbital, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here the electrons are completely filled. So 3d10 also colorless. That is why zinc salts are colorless. Zinc carbonate, zinc sulfide, any zinc salts if you take, it will be colorless. That is because of this D10 configuration. So Cu+, it's called cuprous, it is colorless. Similarly, scandium 3+, colorless. So which are the electronic configuration having 3d0 and 3d10? They are definitely colorless. Other than that will be colored. For example, you can have a doubt. What about exactly off-filled configuration? They are colored only. Manganese 3D5 is a stable configuration for manganese. Okay, so definitely it is having a color, okay, pink color salts, slight pinkish tinge salt it will be. So here what you should understand, what is the concept here? D0 and D10 are colorless. Now how the color of the color is happening, like how? It is because of unpaired electrons. Okay, unpaired electrons, definitely at least one unpaired electron should be there. So when energy is supplied, what happens? The electrons get excited. From the ground state, it goes to the excited state. So from the excited state, it has to come back to the ground state. Am I right? So how much ever the energy we are supplying, depending upon that, it goes to the higher shell, and there it will be there. Again it will come back. So while coming back, how much ever the energy is absorbed, the same energy will be released. So let me explain this. Suppose let us assume that there is one unpaired electron. Okay, if there is one unpaired electrons, what happens? The electrons get excited. Okay, the electrons get excited when the energy is supplied. So when the energy is supplied, what happens? The electron get excited. So it goes to the higher shell, and again it can't be there for a longer time. It has to come back. Okay, so it will again come back. So while coming back, it will release energy in the form of light in the visible region. In the visible region. Okay, so you know Vibgyor, no? Okay, so in the visible region, it gives out the light. So we can see the colors. Okay, once again I will repeat, the electrons initially will be in the ground state. When the energy is supplied to it, the electrons get excited. So it gets excited, it will be there, but it can't be there for a longer time, it has to come back. But while coming back, it will release energy in the visible region so that we can observe the colors. Okay, so this is called d-d transition. What is d-d transition? What is the meaning of that? The electron from the d orbital is going to the excited state, again it is coming back and it releases light in the visible region. So d0 and d10 are colorless. Other than that, all ions, okay, containing the d orbital, definitely they are colored. Is it okay? Hope you guys understood regarding the color, how excitation happens from ground state to the excited state to ground state it comes, and while coming back it releases the energy in the visible region, so in order to we can observe the colors there. Is that okay? Right. So now let us go to the electrode potential. Okay, now we are going to see electrode potential. So what do you mean by electrode potential? So we have a particular chapter called electrochemistry. So there we would have seen like what is electrode potential, like what will happen if it is negative, positive and all. So again we are going to see here. So what is electrode potential? The potential difference which is created between the electrode and its solution. So when you keep the electrode in the solution, so what is the potential difference created? Okay, plus minus, potential difference created between the electrode and the solution is nothing but what? Electrode potential. Okay, and the electrode potential is purely experimental. Okay, it is purely experimental. It's not the theoretical, it is experimental. So it depends upon ionization energy, sublimation energy, hydration energy, enthalpy of atomization. So now like ionization energy, you know what it is, right? Ionization, amount of energy required to remove an electron from outermost shell or valence shell is ionization potential or ionization energy, right? And enthalpy of atomization. What is enthalpy of atomization? The energy supplied to the lattice such that the atom is removed from the lattice. Actually it is difficult, right? It will be bonded with the similar atoms and you are supplying energy and taking one atom out. So that is called enthalpy of atomization. What is hydration enthalpy? So when the salt dissolved in water, it releases energy. That is called hydration enthalpy or hydration energy. Is that okay? So when the energy, so this is hydration enthalpy. What is sublimation energy? The solid, it is changing to a gas, and how much heat is required there. So that is sublimation energy. So on the whole, what I am trying to say is, electrode potential calculation or electrode potential experimentally we are doing, it depends upon all these energies: ionization energy, sublimation energy, hydration enthalpy, enthalpy of atomization. So everything need to be balanced. So in order to get more negative electrode potential. So why I am so specific about this is, with the electrode potential value itself, we can say that whether it is a good oxidizing agent or whether it is a good reducing agent, we can find out from that. Is that okay? So more negative reduction potential it can act as good reducing agent. Okay, more negative reduction potential, that particular element can act as a good reducing agent. For example, zinc, if you take, it has minus 0.76 volts. So like that. So that is experimentally done and we are getting that value. Okay. So more the negative reduction potential value, it can act as very good reducing agent. In order to have more negative reduction potential, it has to have high hydration enthalpy. High hydration enthalpy, low enthalpy of atomization. Okay. In order to have, this is very, very important points. Okay. So any element to have act as a good reducing agent, or an element should have a more negative reduction potential, then it should have a high hydration enthalpy and low enthalpy of atomization should be there. Okay. And another important point is also there, that is the sum of ionization energy and sublimation energy should be balanced by hydration energy. What is it? Sum of ionization energy plus sublimation energy should be balanced by if it's so, then it will be more negative reduction potential and then it will be a very good reducing agent. Is it okay? Now here the important point is about the copper. Generally, if you take the copper reduction potential, it has positive value, okay, 0.34 volts. It has a positive electrode potential value. Supposed to be copper is a metal, no? So it should act as a good reducing agent, but rather than here it is positive. Why? So the previous points we saw, no, that is not followed here. So what is the point here? It should have a high hydration enthalpy and low enthalpy of atomization. But here what happens is it has high enthalpy of atomization and low hydration enthalpy, and sum of ionization energy and the sublimation energy is not balanced by the hydration energy. Because of these reasons, electrode potential of copper is positive. Understand? And also, like for example, if you take Cu plus is not stable in aqueous solution. Whereas Cu2 plus is more stable, okay, in aqueous solution. So Cu plus is not stable in the aqueous solution, that is cuprous. They are not stable in the aqueous solution, whereas Cu2 plus is more stable in the aqueous solution. What is the reason behind that? Again the same reasons. Cu2 plus has more hydration enthalpy. So it is more stable in the aqueous solution when dissolved in water. Okay, more hydration enthalpy. Whereas Cu plus, they have less hydration enthalpy when compared to Cu2 plus. So what I am trying to say is Cu2 plus is more stable in the aqueous solution because it has high hydration enthalpy when compared to Cu plus. And this reasons also the same reasons. Ionization energy and sublimation energy is not balanced by the hydration enthalpy in the case of Cu plus. That is why Cu2 plus is more stable in the aqueous solution. Understood? So electrode potential, so based upon the electrode potential values, we can decide whether an element can act as a good reducing agent or not. So in simple shortcut, more the negative reduction potential, it can act as a good, more negative reduction potential, it can act as a good reducing agent, more positive or less negative, it will act as a good oxidizing agent. Okay, understood? So now we are going to see the oxidation states. Okay, next topic will be oxidation states of transition elements. Okay, that's what we are going to see next. Oxidation state. So generally when you compare D block elements and P block elements, D block elements have variable oxidation states. Okay, generally D block elements have variable oxidation state. Okay, D block elements have variable oxidation states when compared with P block. Why? So D block elements have variable oxidation states when compared with the P block elements. The reason is D block elements contains D orbitals, right? P block elements contains P orbital. So P orbital has only 3 boxes, 3 orbitals, whereas D orbital consists of 5 orbitals. Am I right? So more unpaired electrons possibility is there. So maximum P block elements can have how many unpaired electrons? Maximum only 3. But whereas D block elements can have maximum, it can go up to 5, right? So generally what is the answer for this? D block elements has D orbital, right? D orbital which consists of 5 boxes, 5 orbitals, whereas P block elements contains only 3. Okay, if you take P orbital, only 3. So maximum unpaired electrons can be 3 here, whereas in D orbital it can be maximum up to 5. So more the unpaired electrons, more the oxidation states it can show. That element can show maximum oxidation states. So if you go till the middle, okay, scandium, titanium, vanadium, chromium, manganese, cobalt. So iron will come next to cobalt. Iron, cobalt, nickel, copper, zinc. So if you consider these elements, it can have only one oxidation state. So it can have like +4, +3. So here you can see +3, +4, +5. So here it can show +3, +6. These are the stable oxidation states, whereas manganese can show +2, +4, +6, +7. Iron +2, +3, +2, +3, +2, +3. Here +1, +2, +2. Now you can see till the middle, the oxidation state increases and then it decreases. Am I right? So what you understand from this? When it goes to the middle, the number of unpaired electrons increases. So the oxidation state is directly proportional to number of unpaired electrons. Number of unpaired electrons. This is the main important point. Okay, more unpaired electrons, more it can show oxidation states. Now you come to the middle, manganese. Manganese has 3d, 5 and 4s2, right? So it has like totally 7 orbitals, total I am saying. So d orbital is 5 and then 2. So it has maximum number of unpaired electrons, 5 possible, right? So 3d, 5 and 4s2. So it can show maximum number of oxidation states, more unpaired electrons, so more oxidation states. Whereas zinc, if you take zinc, everything is completely filled. So maximum it can have only 2, only one oxidation state, that is +2. Any other oxidation states, they are not stable. So what do you understand from that? Oxidation states are directly proportional to number of unpaired electrons. So more unpaired electrons, more it can show oxidation states. And one important question to you guys. So KMNO4, suppose if it is in +7 oxidation state, for example, I will show like one compound, well-known compound, okay, KMNO4. If you calculate the oxidation state, okay, so potassium is 1 plus 4 into -2 equal to 0, x minus 7 equal to 0, x is equal to +7. So what is the meaning of +7? All electrons is lost completely, am I right? Because it is 3d, 5 and 4s2. If it is +7, all the electrons are lost, correct? So if all the electrons are lost, so it is 3d 0, it's supposed to be colorless, but it is colored only, right? What is the color of KMNO4? The color of KMNO4 is purple. So that purple color is because of ligand to metal transfer. Ligand to metal, what transfer? Electron transfer. There is a reason. Okay. Here oxygen acts as a ligand, it donates its electrons to the empty orbital of manganese, because of which it gives the color. Excitation of electrons takes place and it gives the color. But actually speaking, here it is ligand to metal transfer, it is not purely because of the dd transition, which is already, no d orbital there, no electrons there. Is that okay? D electrons is not there. So it is because of ligand to metal transfer, it is not the dd transition. So I am making it very clear because in many competitive exams they are asking questions based on this. Okay, even K2Cr2O7, potassium dichromate also. Actually it is orange in color. Here also chromium will be in +6 oxidation state, because of ligand to metal transfer there is a color, I mean that orange color is observed there. Is that okay? Right? So oxidation states, all of you understood? So oxidation states is nothing but it depends upon the number of unpaired electrons. Okay, how much ever the electrons is lost, but unpaired electrons is, plays a major role in getting the oxidation states. So from scandium to zinc, if you see till the middle it increases and then it decreases, because the number of unpaired electrons in the middle increases and then it decreases. Okay, hope you guys understood oxidation states. Yes, thank you students.